Now. Okay,
So I was curious
just a
on,
second, William. Let me say something at the beginning here. This is Wednesday, April 1st. I'm recording the interactions I have with students so that students can access them no matter when they're able to log in. And William Anderson is up first. So, William, go take it.
so I was curious on number 5 in the homework, or I believe number 17 in the book. When I was looking at the example, they show taking the derivative of, uh, let's see, of a sub k. And I was curious why you take the derivative of it, because I don't remember seeing that in the video.
Yeah, that is a really good question. Um, Number 17.
Yeah.
So it's the one that has k squared over k cubed plus 1.
Yeah, my example is k over 12k to the 7th, so similar.
Similar but weirder. Do you
Yeah.
have a -1 to the k plus 1? Oh, of course you do, because it's the section is alternating series. All right. Well, interesting, William. You've grabbed a hold of something that the calculus professor mentioned early in a theoretical sense, but the videos I watched, he never said one word about later. And I almost made a separate video just to kind of dig into that a little bit. So let me tell you, and then we'll discover why the derivative might come in handy. Remember, the alternating series test, in order to use it, you have to know that three things are true. Number one, the formula AN always cranks out positive numbers. So the alternating is only done by that -1 factor. So I always need positive numbers. The second thing, they have to go to 0. We've known that since we started, right? The divergence test. And for alternating series, it's no different. The terms have to go to 0. The third condition, which he mentioned, is that at least eventually, maybe not starting at the very first term, but eventually they have to, the sequence AN has to be a decreasing sequence. Okay, so we need to be sure that at some point beyond that, the next term is smaller than the previous term. And of course, they're all going to 0. We figured that out. So he mentioned that condition when he stated the alternating series test, but according to what I watched, never once did he talk about it working through the examples. So I guess, and he didn't even say why he was ignoring it. I mean, he might say something like, and that's basically true, like for the series we'll see, if there is no cosine or sine involved, eventually it's going to be a decreasing sequence. We just don't have the functions. If given that the terms are going to 0, we just don't have the functions that are so complicated that they can't make it just sort of naturally decrease to 0. So on this problem where the derivative comes in handy, remember the derivative can tell us when a function is increasing and when a function is decreasing. So what we want to make sure is the function, the one I have on problem 17. Let me put it on the board here. Actually, tell me your problem. Just the function part.
The a sub k is k over 10k to the 4th plus 1.
Okay, we need to make sure, clearly that goes to 0, first degree polynomial over a fourth degree, no issues there. But we need to make sure that eventually it starts to decrease. So we're going to use what we learned in Calc 1. We're going to trade sequence for the corresponding function, which is that one, right? We'll take its derivative. I want to show it eventually is a decreasing function. And the way we'll do that is we'll show that eventually the derivative turns negative and never becomes positive. Okay, a negative derivative implies a decreasing function, right? We learned back in what, chapter 4, maybe. So we'll use the quotient rule here. Make it sort of messy, but we won't panic. all we really care about is the sign. So the quotient rule times 1 minus x times 40x cubed. Well, that's kind of a daunting expression, but most of the time it works out pretty nice. We'll keep the denominator. Notice here we get 10x to the fourth, and then we lose 40. So I have 1, that 1, minus 30, plus 10, minus 40. Okay, William?
Yep.
Yeah. So pretty clearly, this is going to turn negative. In fact, it's probably negative from the get-go for us. That is, as soon as x cubed becomes bigger than 1/30th, this thing's negative. Right? This guy's a constant. And we just need to make this bigger than 1. And it is from the beginning. I mean, if x equals 1, this is a negative number, and it's going to stay negative forever. So this is less than 0 for all x's bigger than or equal to 1. And therefore, this is a decreasing function. That's why they use the derivative, to verify that third condition.
Okay.
Can you see the board okay? For some reason, when I talk, it usually makes me big, and it's leaving me small.
I believe that's because you're in speaker view. If you go up to the top right corner, there should be a little box, and it should say like gallery view or something like that.
You not see me, or?
I see you.
Okay, there.
Yeah, if you select gallery view, then you can see everybody.
Yeah,
But I can see the board just fine.
Okay, if I get my head out of the way. So what I wish the calculus professor would have said, and it's basically true, it's what I think I said a little bit ago. Really, I mean, that condition has to be true. If it's not true, we could construct an alternating series where, you know, ignoring the -1 factor, all the terms are positive, they go to 0, but it does not converge because the third condition is not met. Now, it's pretty tricky to construct one, but it's possible. And so we do need to make sure that third condition is met. And I think the reason why the calculus professor ignored it is because, like I said before, unless there is a trig function involved, if the terms go to 0 and they're always positive, eventually they're going to have to decrease. Our functions aren't that complicated. You know, polynomials or exponentials or whatever they may be. So technically, well, if there's no sine or cosine, probably we can ignore that third condition. Now, if I put it on a test, I would like for the student to say something about it, and maybe just say something like, clearly, the terms are eventually decreasing, just to show me that you know that there's that third condition that we can't ignore, but most of the time, it's not going to cause us any problems.
Okay.
Okay, good question. And I mean, that was the most questionable part of the whole thing, and you grabbed a hold of it right from the get-go. So good for you.
Okay. So then, alternatively, when it's sine, then it won't converge, or it'll just get infinitely smaller.
Yeah, another super good question. Of course, it depends on how exactly the sign is involved. I would say that very likely, and I can't say definitively unless you show me a specific formula, but I would say generally the series is going to converge, but the alternating series test can't prove that. Right? We can't use the alternating series test unless all three of those conditions are true. And so my guess is, because we can't guarantee, you know, here's maybe a simple example. It needs to alternate. So there we go. Because I added the 1, those terms are never negative, so the first condition is met. They go to 0. 1 plus sine k kind of oscillates between 0 and 2, but the k squared on the denominator is going to infinity, and that'll pull the whole thing back to 0. But because of the sign, it certainly is not obvious that this function becomes decreasing. Now, we could do what we did over here. We could calculate the derivative, and maybe we would find out that it does become negative, the derivative, and therefore that function becomes decreasing. But my guess is we're not going to be able to verify that. And but almost certainly, I mean, I know for a fact that series converges, but the alternating series test can't prove it. If I'm going to prove it, I need to use some other test.
Okay.
Okay?
Yeah.
So when the alternating series test doesn't work, then we don't know. Okay, like if those 3 conditions aren't met, then that doesn't guarantee divergence. It just means this test isn't going to settle the issue for us. With one exception, and the second condition, if the terms don't go to 0, it diverges, right? Case over by the divergence test. If the terms don't go to 0, it's got no chance, and that's one of the very first things we learned about series. It's always true, whether the terms are positive or negative, alternating or randomly positive or negative. It doesn't matter. If the terms don't go to 0, the series diverges. Okay?
Okay.
So I don't know if I'll mention to the calculus professor when I see him that he kind of forgot. I wish he would have at least said, you know, the condition has to be met, but it's not, but it's going to be met for all the problems I assign. And then, okay, we can ignore it. Everything was wonderful. But like I said, I can show you an example of a alternating series where all the terms are positive. They go to 0, but it does not converge because we don't have that decreasing.
Okay.
And it's tricky, but you can do it. And that's all we need to know right now. We'll save the tricky stuff for later. Do you have any other questions?
I think that was just about it.
I have one for you.
All right.
So I posted a video that I made, just kind of a summary of chapter 10. Did you view that?
I looked at the Foxtail this morning and I saw that it was there.
Okay.
I didn't watch it yet though.
All right. Well, I wanted to make sure there actually is no assignment from it. Let me check something here real fast. Okay, now I'm up to 6 views. That's pretty good. Yesterday there was only 1 view and I was a little disappointed about that. But it's up to 6. And I see in the book there actually is a section. So I'm going to add some homework problems. It's section 8, where they just kind of talk about, okay, we got all these tests out there. How do we use them? And so in section 8, there's really nothing new introduced. They're just kind of stepping back and saying, okay, here's how we might go about using. You know, when you have on the video, you'll see there are kind of 10 ways that we've discovered that help us determine the behavior of a series. And, you know, that's good. That's a lot of power. But when it comes to choosing one, like, how do you do it? If I only had 1, then I know, well, let's use that method. But when you have 10, it can get sort of complicated. And therefore, that's kind of what that video is about. Just, first of all, I list them all out on one screen, all 10 of them, and not the details, but the name of it. And then I picked 4 problems, I think, out of actually the review. I don't know if I should admit this, but I didn't actually know there was a section in the book where this is exactly what they do. So maybe I'll go to page 703, chapter 10, section 8, and add a few problems on Pearson, or at least encourage you to work them as we head into an exam next week. All right, anything else?
I think that's it.
All right, well, thanks for stopping by, and I'm going to be here for a while if something comes up, if you're working on your homework.
All right.
Maybe silent. I'm going to pause the recording just so it doesn't get super long if there's nothing going on. And I'll be back again on Friday, same time. And also, something comes up, shoot me an email if you have a question.
Cool. Thank
All
you.
right. We'll see you, William.
See you.
Yep. Bye.
Bye.
Awesome.
All right. Elijah has a question for us.
All right. Yeah, I've written 3 down.
Okay.
So the first one, in the video that you posted on YouTube about the review, you mentioned a specific example where it was distinct whether or not you needed to use the comparison test or the limit comparison test, and that involved sine or cosines. And I was wondering if we could go over something like that. I don't remember seeing that in a practice problem yet. I might be mistaken.
So when sine or cosine is involved?
Yeah, in the series.
Yeah, so let me see if I can find an example. It may be that I want to think about it and make up my own if I don't see a good one here.
Yeah.
So let me try this. If it doesn't work, I'll apologize. I don't know how to erase part of the recorded video, so it'll just be out there for everyone to see. But let's give this a shot. 1 plus sine k over k squared.
All right.
Okay.
Let's give it a shot.
So, because sine, just trapped between -1 and 1, I added the 1 here so that it's never negative. That's the main reason. Because a lot of our tests require positive numbers.
Yeah.
The sine, it doesn't blow up. It just goes back and forth. So when I look at this thing, I say, it's really going to behave like a p-series. Do you see that with p equal 2? Because
yeah,
if it went to infinity, then I need to pick a different p, or maybe not even think of it as a p-series. But because this is kind of stuck, and not kind of stuck, it is stuck between 0 and 2. So I'm going to compare it to, actually I'm going to limit compare, and I hope that it's not going to work. So then we can see the problem the sine causes. We're going to compare to this one. So we take the limit as k goes to infinity. The series we know goes on the bottom. The series we don't know goes on the top. Which is the limit. Notice those k squareds just cancel right out.
Yeah.
And it leaves me with 1 plus sine k. And what do you know about that limit?
Well, sine limit as k heads to infinity of sine k is 0. So that goes to 1.
Okay, think about it for a minute. Going to infinity, not 0. So the sine,
it fluctuates between -1 and 1.
So this limit
would be, it would be between 0 and, I see what you're saying.
doesn't exist.
Okay.
That function does not have a value. Right? It just between 0 and 2. So the limit comparison failed.
I see, because it doesn't head towards a certain value.
Yeah.
Okay.
And why did it fail? Because of the sine.
Yeah.
Well, that's what I mentioned. If sine or cosine is involved, then the limit, now let's use the ordinary comparison. So because of the numerator, I'm actually going to compare to I need to account for that. So we're going to compare to the series 2 over k squared.
Mm-hmm.
Does that series converge or diverge? Do you know?
That must converge.
It does. It's a p series. P equals 2. Multiplying by 2, it's just going to double the value it converges to. It's not going to change the
Mhm.
behavior. So this guy converges. We know it's a p series. And then I'm going to say, okay, sine. Now I have to prove an inequality. I mean, that's why the comparison is
Right.
first go-to comparison test, because we don't have a lot of experience proving inequalities. In fact,
Right.
we really haven't applied any calculus to it. You have to think about what you learned back in maybe pre-calculus. But we do know sine is always between -1 and 1.
Mm-hmm.
Our series has 1 plus, so add across that 1, and I get 1 plus sine k is always less than 1 plus 1. 2.
Well, would it be less than or equal to 2?
Okay, I can go with that. It won't stop me from using the comparison test.
That's right. Yeah.
Only way that it could be equal to 2 is if k is a multiple of pi
Mm-hmm.
and k is an integer.
Oh, okay.
In theory, it could be as big as 2, but it's not going to be because we're restricted to plugging in integers. And
Yeah.
as you know, the period is an irrational number, 2 pi. It's not an integer. So, but it doesn't matter. We can still use the comparison test. So if you don't want to think about that, just write less than or equal.
Right.
Now multiply through by k, actually divide by k squared. I'm trying to build up this thing here with knowledge about it.
Right.
Do you see now that we've done it?
Mhm.
The term.
Well, actually, I can't see the very bottom of the board.
There you go.
There we go.
So the terms of the series that we don't know of behavior for, we can prove just using this nice little property of sine that all of them, you know, a 1-by-1 comparison are smaller than the corresponding terms of this series, which converges.
Right.
All of these guys add up to a finite number. All of these will add up to a smaller finite number, and
Yeah.
that settles the issue. It converges.
Right.
Okay.
So that sum we compared it to converges, and this sum is, and the sum we're looking at is always less than that sum.
Yeah.
So it must converge as well.
If this inequality is flipped
That-
around, it would be of no use whatsoever.
Yeah.
That's why we picked the 2. I mean, if I didn't have a 2 here, if it had a 1 there, just like the normal p series, then this sign would have to go the other way, and that wouldn't help us at all.
Right.
And then look at 1 plus sine k, and we think to ourselves, it can never be bigger than 2.
Mm-hmm.
And so we can pick a converging.
Yeah.
So
All right. That makes sense. That's good. All right.
you had 3 questions.
I do have 2 additional questions. Just boxing this box for the answer right here. So the other 2 were just like tests when I wasn't sure where I hadn't used them as much, and I was just not sure when to use them. The first was the root test.
Uh-huh.
There was a couple on the chapter review that looked like I was like, oh, we might use the root test, but we didn't. We did not use it on any of them.
Yeah.
And one of those was number 58 that we did.
So that's k to the minus k. Yeah, I did the ratio test, right?
Yeah.
Yeah. You can do the root test there. There is one piece of information that I don't remember if we discovered it. The calculus professor used it in one of his examples. I think it may have been on the alternating series. So let's do it, and we'll see if that missing piece of information, if it makes sense to you. So, and we want to use the root test. So we would never ever use the root test unless our formula had something raised to the kth power.
Right.
We like to make life easy for ourselves, and the kth power, the kth root of the kth power is super nice. So here's what we do. We calculate L, the limit as k goes to infinity, kth root of k e to the minus k. Because the limit as k goes to infinity. The root of a product is the product of the kth roots. We use that a lot for square root, but it's true for all. Okay?
Yeah.
The limit of a product is the product of the limits, if they both exist. And what is this thing over here?
That's 1 over e to the k.
The kth root of that is?
1 over e.
Yeah, let's write in what you said. And then we'll simplify it in the next step.
All right.
All right. So you told me this is 1 over e. The limit of a constant is the constant.
Yes.
So now, this is the limit I was talking about before. You may have seen it.
I think I recognize it.
He writes it like this: k to the 1 over k. Do you know that limit?
K to the 1 over k.
This,
Um,
you remember seeing it in one of the calculus professor's examples?
I don't recall.
Yeah. So
I swear I recognize it though.
the form is infinity to the 0. This is going to infinity, that's going to 0, which is one of those indeterminate forms. So using L'Hopital,
Oh, right.
we can settle the issue. But how about if I just tell you?
Sure.
Using L'Hopital's rule, you get 1.
Okay.
Okay? So
Super easy.
1 slides in there. Our limit is 1 over e.
Yeah.
Now, this is the root test. How do we interpret that 1 over e?
It is less than, or no, it's greater than 0 and less than infinity.
Okay, that
Or is that the
comparison. It's okay
Oh, okay.
for the test.
Let's see. I know I have it written down. See if I can find it. Should memorize it though. Okay, it's between 0 and 1.
Yeah, it's less than 1. Therefore,
it converges.
converges by the root test. Yeah, we need to be less than 1. It converges.
Converges.
Okay, so we just did this by the ratio on the video. Sorry, by the root.
Yeah.
Video, I use the ratio test. I think I mentioned on the video you could also use the test. You'd have to integrate by parts, but we know how to do that. Yeah, those are the only 3 that I can think of at the minute. Moment. We could probably devise a way to use a comparison test, but it would be a little clunky. Okay.
All right. That was oddly enough, I was gonna also ask about the integral test because I haven't used that one for a long time.
You have a,
But here, I was gonna grab a drink of water real quick. I forgot to fill my water bottle. I need it for every class, so
yeah,
I'll be back in 30 seconds.
all right.
All right. Here I am.
All right. Do you have a specific example? I can give you one. But if you
Hmm.
have the homework, that might be better.
Yeah, I'll see if I can. Let me pull up an old homework assignment.
Okay.
Um, It's going to take a minute to log into Pearson. I never remembered my password. I just wrote it down on a
Oh,
text document in my computer. Hopefully no one finds it because then they'll find all my other passwords too.
oh yeah.
But
Yeah, passwords are a pain, but I guess they're necessary.
very necessary.
Although your Pearson homework, I don't know if the scammers are out to get that.
Not that particular information, I don't think. Okay. I believe it was it section 10.4?
Say it again.
Was it section 10.4?
That sounds right.
All right.
Long section.
Mhm. Might be 10.5.
2.5 are the comparison tests.
Hmm. Oh, it was 10.4. All right. I'll just have to hunt one down.
Now, looking back at 10.4 now, the ones we could use the integral test on, I think we know better test from later in the chapter.
Yeah.
Do you have your book open?
I'm using the online book.
Okay, so let me just write these on the board. We can do
Yeah.
it. Well, here's one we could use the integral test on, but we probably have a better way to do it. 1 over square root of k cubed.
All right.
Well, as an integral test, we would say, you know, some sort of triviality where it starts. If we could find what the series converged to, then it would matter the k value where it starts.
Right.
Since we're not finding the sum, it doesn't really matter. I don't know if you saw the calculus professor, a lot of times he won't even write this index information. So we're going to go from
Yeah.
we're going to think of this function 1 over k to the 3 halves. And so we'll call it x for the integral, which is the limit. It's an improper integral. So we'll stop at b and then let b slide off to infinity.
Mm-hmm.
X to the minus 3 halves. Can we integrate that?
Yes, we can. That's okay. That gives me a second to work backwards. That's -1/2 over -1/2, or to the power of -1/2.
Yep.
Yes, there it is.
So let's take the constant through the limit, -2, just to make life a little easier. And then we have 1 over the square root of x, the function piece. So we're going to plug in b, and when I plug in 1, I just get 1.
Mm-hmm.
What's that limit?
Just +2.
+2. What does +2 mean for the integral test?
That it converges.
That it behaves the same, the series,
Right.
as the integral. Since the integral converges.
So we've actually solved the series as well.
Well, that's what we're working on. Absolutely.
That's awesome.
Yeah, we have the series and we think, well, let's try an integral test, and we work it out, and works out perfectly.
So how do we know when the series and the integral have the same behavior? What are the criteria again?
Good question. This integral converges, the series converges.
Okay.
Trading this chapter 10 problem off for a chapter 8 problem.
Yeah.
Find out if the integral converges. We learned how to do that in chapter 8. We know how to do it. And so, and when we get done, we're either going to get a finite value here, or we're going to get that this limit doesn't exist. Maybe it's plus infinity, or it could be like the sine one just never approached. If this limit exists, this series converges. If it does not exist, it diverges.
Gotcha.
Okay.
And then if it does not exist, the test also fails?
Yes.
Okay.
No.
Oh.
If the integral doesn't exist, the series diverges.
Oh. So that is, so that in that respect, it's a little bit more helpful than like maybe the divergence test, where, you know, we can tell like whether we get a finite value or not, the behavior.
Yeah, the divergence.
Exact behavior.
One thing happens, it settles the issue. If it doesn't happen, then we don't know. You're exactly
Right.
Yeah. Now, we've been a little bit careless here, and I encourage you when we're done to watch the first part of the video we're recording right now, because William asked a super good question right off the bat. That is, these tests, a lot of them, they have conditions. Like if this is true and this is true, then we can run the test. A lot of the tests say you have to have positive numbers, right? For the integral test, this function, it needs to be positive. That's not a problem here. It's actually, we're looking at this function, 1 over x. But remember that it has to also eventually be decreasing. And we didn't think about that here. We just launched calculation. Now, 1 over x to the p, if p is positive, they're all decreasing. So
True. Right.
maybe we didn't think about that here because it was so obvious. But if the function is more complicated, before we can apply the integral test, we need to make sure that the function is eventually, it doesn't have to be it at the beginning, but eventually beyond, you know, some fixed point, it needs to be decreasing. And William's first question was like, how do you decide if a function's decreasing? If it's not obvious, like maybe this one.
Yeah.
And so we talked about that, and maybe I gave him a good answer. And part of the video. Okay.
I will definitely check it out. All right. Well, it looks like you said, there's some more powerful tests for this specific series, you know, like the p-series test.
Yeah.
But yeah,
so,
makes sense to me.
Yeah. So like I said a little bit ago, by the time we finish chapter 10, we probably have enough tests that the integral test is not like super powerful one.
Yeah.
But I mean, the example I was going to give you a little bit ago, that I think the integral test is maybe the best one to use on is this one. 1 over k log k. Let's go from 2 to infinity.
Mm-hmm.
Okay, it's not a p series because of the log. I think the ratio test will fail. I think it would get us 1, which is, the one thing that happens where the ratio test doesn't work. The terms do go to 0. Both k and log k go to infinity. So,
Mm-hmm.
if you think about it, I was going to say the word compare, but I don't want to use the comparison test. So if I put these side by side, like 1 over k to the p, let's write p as 1 plus any positive. If p is positive, that thing converges. We just need to get the power a tiny bit bigger than 1, and then it converges, right? So you might think, well, heaven, and we can write this as k to the first times k to the p, and this thing is going to go to infinity. So it's just like k all by itself. That one diverges. That's the harmonic series, but it just needs a little bit of a boost, and you would think that ln k would be enough of a boost. It goes to infinity. But let's try the integral test. So we'll integrate from 2 to infinity, 1 over x log x. It's a little bit tricky here, but if we substitute for ln x, then the differential will wipe out this x. Notice how that works?
Yeah.
So we get the integral of 1 over u du.
Oops.
Next is 2.
It's much easier.
And the log does go to infinity. So if we change the limit so we don't have to substitute back. Oops. This should just be b. Still trekking off to infinity.
That's pretty easy to integrate.
Yeah, so we get the log of u.
Yeah, natural log u, absolute value, of course.
Yeah, but of course, everything is positive here.
Mm-hmm.
So the natural log of u from ln2 to b. Which gets me ln b minus ln2. Can you see that?
Yeah, and that does not exist,
Infinity, you're right.
which means that it diverges.
This integral diverges, therefore, the series.
Mm-hmm.
So it's just fascinating to me. I mean, you pay up by something that's going to infinity. It's getting big, and it doesn't have to get, for every positive number p, this integral converges. We just need that power to be a tiny bit bigger than 1. And you would think that ln k would do that for us, but it doesn't.
Huh.
Okay?
It's really strange.
It is strange. Infinite
Very
series,
unique.
strange and wonderful.
Yeah. Okay. Well, those were some great answers. I'd highly recommend the help session to anyone who is struggling with anything. So I'll text a few friends who I know are.
All right. Especially, I mean, you're trying to change it, and I hope you do. But right now, it's like one-on-one tutoring. So go for it.
Yeah. All right. Well, have a good one, Professor Johnson.
Elijah, thanks for checking in.
Yeah. See you later.
Bye.